All right, I'm going to finish up the ELISA test problem. I'm also going to start it from the beginning. Those of you who are in third hour, we talked about how messy it was. However, we did get through A, we got through B, we just didn't get through C. I started it and then I was like, oh, we don't have time to finish. The bell was going to ring in a minute. Hour 4, you didn't get to see it at all. This is your chance. The ELISA test, whether a patient has contracted, ELISA tests whether a patient has contracted HIV. The ELISA is said to be positive if it indicates that HIV is present in a blood sample. And the ELISA is said to be negative if it does not indicate that HIV is present in the blood sample. Instead of directly measuring the presence of HIV, the ELISA measures levels of antibodies in the blood that should be elevated if HIV is present. Because of variability in the antibody levels among human patients, the ELISA does not always indicate the correct result. As part of the training, staff in a testing lab applied ELISA to 500 blood samples known to contain HIV. So this is our first hat. In that hat, if I would draw names out of them, 489 names. Now remember, this hat, these people have HIV. And that's what it says here. It's known to contain HIV. So these 500 people, they all have HIV. The ELISA test was positive for 489 of these. So this is positive, given they already have HIV. All right, which means 500 minus 489 is 11. So in this hat of people who already know they have HIV, they're testing the ELISA, and we know that 11 of them test negative, even though we know they already have HIV. Okay, next, as part of that same training program, the staff also applied the ELISA to 500 other blood samples known to not contain HIV. So this is our other hat, 500 with no HIV. The ELISA test was positive for 37 of them. So 37 of these people who don't have HIV, okay, 37 of them tested negative. And then 463, so these people tested negative. 463 out of 500 tested negative. Sorry, they tested positive, sorry. So again, what just happened in this hat of 500 people who are known not to have HIV, 37 of their blood samples tested positive, 463 of the 500 tested negative. Part A. When a new blood sample arrives at the lab, it will be tested to determine whether HIV is present. Using the data from the training program, estimate the probability that the ELISA would be positive when it applied to a blood sample that does not contain HIV. So this is a given now. That goes in our denominator. Out of all of the people who do not have HIV, 500. That's this hat right here. What's the probability that they are going to test positive? Well, we know that right here. They test positive in 37 of them. So 37 over 500. And 37 divided by 500 is 0.074. All right, next. Among the blood samples examined in the training program that provided positive ELISAs. This is now our given. All we care about now are the people who tested positive ELISA tests. So what does that mean? We can test it 2 different ways. There are 463, scrolling up, I'm sorry. There are 489 people who tested positive for ELISA from the group that has HIV. So we're going to put that in my denominator. Plus, we have 37 people, which is right here, who tested positive from the group that does not contain HIV. 489 plus 37 gives me 526. Okay, so what does that mean? Those are the 526 people who tested positive. That's what we care about. That's the given among the blood samples who tested positive for ELISA. what proportion actually contain HIV. So out of this group here, this 526, who actually have HIV? Well, scroll up, this 489, they're the people who actually have HIV. So we put 489 up here, and that's my answer, 489 over 526. You can leave it as a fraction, or you can write it as a decimal, which is 0.9297. Okay, the last question, which is the messiest by far. I'm going to take a picture of it and go to the next page. There's a lot of junkies that you don't need to worry about at first. At first, you want to just read down and say, okay, what's going on? Okay, so when a blood sample yields a positive ELISA result, 2 more ELISAs are performed on the same blood sample. If at least one of the 2 additional ELISAs is positive, the blood sample is subjected to more expensive and more accurate tests to make a definitive determination of whether HIV is present in the sample. Repeated ELISAs on the same sample are generally assumed to be independent. Under the assumption of independence, what is the probability that a new blood sample that comes into the lab will be subjected to more expensive tests if the sample does not contain HIV? Okay, so this is what I was getting to in class for 3rd hour. I was starting here. We're dealing with a given. The given condition is we know that the sample does not contain HIV. And there's 2 things that could happen. So looking back at the people, oops. Looking back at this, we want to say, okay, how is that happening? So we have 37 out of 500. And we have 463. These are all the people here that don't have HIV. Again, I'm going to read it. Under the assumption of independence, what is the probability that a new blood sample that comes into the lab will be subjected to more expensive tests if that sample does not contain HIV? So what we're dealing with right now is all the people that we know are our given condition is we have 37 out of 500. These people test positive, okay, but they don't, are given they don't have HIV. Okay, next, 463 people out of 500, they test negative, given they don't have HIV. I'm going to change these numbers to a decimal because it's going to make it easier. So I'm dealing with all the people that don't have HIV. 37 divided by 500 is 0.074. 1 minus that is 0.926. Okay, next. Now what do we do? Now we have to say, under the assumption of independence, what's the probability that a new sample that comes into the lab will be subjected to more expensive tests? Okay, so what is the more expensive test? When a blood sample yields a positive result, 2 more ELISAs are performed on the same blood. If at least one of the 2 additional ELISAs is positive, the blood sample is subjected to more expensive and more accurate tests to make a definitive determination. So what this means is, given they don't have HIV, so we're only dealing with these numbers, this would be the probability that the first test is positive. Then, and the second test is positive, they're going to get more, testing. All right, so where is this coming from again? If they test positive, where does it say? 2 more ELISAs are performed. if at least one of them tests positive, they're going to get more testing. So that's one way we could get more testing right here. The first one is positive, and then the second one's positive. So then it needs more expensive testing. They're not even going to give that third test because this was positive. So at least one of the two additional is already, like, we're already getting more tests. Or the probability the first one is positive and the second one is negative, okay? But then the third one has to be positive. This again is at least one of the two that they perform after that first one. What is that? So at least one, they're going to get more expensive testing. So there's two different ways this can happen. So remember, this is all for people who do not have HIV. Two positives are right here. I'm going to take 0.074 times 0.074 plus, now I have 3. Remember, this is a sequence of events, so we're doing the multiplication rule. Why did they put in there that it's independence? Because then there's no conditions on this second one. It's just the same probability. Okay, now the probability that the first one is positive is 0.074. The second one is negative. That's going to be 0.926. The third one is positive, 0.074. I'm going to multiply 0.074 times 0.074 plus, and then I'm going to add, so I'm going to add these two products together. I'm doing that in my calculator now. Give me 1 second. And that's going to give me 0.0105. And that's my final answer. What lesson can be learned from this? When there's a lot of junk in a problem, go down to the very end and say, okay, what's happening? And that's what we started in third hour. Ignore all the top. Well, we read through it, obviously, but we go down to the bottom, and we're dealing with the people who do not contain HIV. The people who do not contain HIV are right here, and we figured out the different probabilities. Then we just had to go to the top and say, okay, what's happening? Am I going to get more tests? I have to test positive the first time in order to even be considered for additional testing. They're going to give me 2 more tests. If my second test is positive, automatically I get more expensive testing. Why? Because at least one of the two, so there we go, one of them tested positive, we're going for extra testing. Here, I test positive, I need 2 more tests. The second one's negative, so we're not getting additional testing yet. But the third one is positive again. We need more expensive testing. Here are my probabilities that I got from over here. Multiply and add, and there's my final probability. Thanks, guys.